Alright, so hello everyone. My name is Stephen. I work here at the University of Toronto with Sajeev John. So today I'm going to be talking to you about polymer solar cells. If you're not familiar with polymer solar cells, I'll start off by sort of bringing you up to speed, talking about the current state of the art. And then I'm going to tell you about the 2D metallic grating structure that we looked at. I'll give you some results from 2D numerical simulations that we did. I'll do a brief comparison with a state-of-the-art tandem cell, and then I just want to show you some recent results that we have with a sort of 3D structure, a 3D conical core. So to start off with, polymer solar cells, they're cheap, they're lightweight, they're flexible, that's great. They do have low efficiency though, and they also suffer from photochemical degradation. So the highest efficiencies to date in a polymer solar cell are 10.6% for a tandem cell and 10.1% for a single junction. Here's the sort of IV curve for that 10.1% cell, so you can sort of get a feel for how these cells perform. So for optical modeling, we use finite element method to solve Maxwell's equations in the frequency domain. Basically, you get an absorption spectrum, and we can differentiate between absorption in different regions of the cell. And then we integrate that against the AM 1.5 spectrum to obtain what we call the maximum achievable photocurrent density, MAPD. So we do this integration from 350 to 1,000 nanometers and 2 nanometer step sizes, and that's sort of our figure of merit for all these calculations. All right, so one thing that's happened recently with polymer solar cells is that people have started using these low bandgap polymers. It used to be that the polymers that were used in these cells sort of didn't absorb at very high wavelengths. They would only absorb up to maybe 650 nanometers or so. But now people are looking at these low bandgap polymers that absorb up to, say, 900 nanometers. So the one that we decided to study is called PDTP-BFBT blended with PC71BM, which I will just call PDTP. And the record efficiency for a PDTP cell is 8.1%. Basically, people haven't done a lot of optical studies of this material yet, so we thought it would be worthwhile to sort of see, what can we do optically with this polymer. So to start off with, we just looked at a planar cell with these sort of geometrical parameters. The active layer of PDTP is only 100 nanometers, and it's important with all polymer cells that the active layer not be too thick, otherwise the charge collection efficiency just goes to zero, but in particular with PDTP, it really can't be much more than 100. So we simulated this cell, and we got an MAPD of 22.0 milliamps per centimeter squared. And just as a sanity check, we can compare that with experimental values. We looked at, there was one cell that had the same geometry, and the short circuit current density was 18.6 milliamps per centimeter squared. So that would correspond to a charge collection efficiency of about 85%, which is right in the right ballpark. So we think we can trust this number. All right, so this is the structure that we wanted to look at. You can see it's the exact same layers. We have glass, ITO, zinc oxide, PDTP, a thin layer of aluminum oxide, and then silver. But if we look at this sort of trapezoidal metallic grating structure. And so one thing that's nice about this structure is we have a conformal layer of PDTP, so the thickness stays at just 100 nanometers. So this design would not necessarily come at the cost of electrical performance. And so, and we also look at, we add some triangular corrugation to the top of the cell, just to sort of see, how much benefit we get from really good anti-reflective coating. So the first thing we looked at was, all right, let's see what the best period and height of the grating would be. So shown here is the percentage enhancement in MAPD as a function of the grating height, and then all these different lines represent different periods for the grating. So we looked at grating heights from 400 nanometers to 2 microns. In the sort of lower left corner here, we would have your sort of fairly low aspect ratio gratings. So we would have a height of only 400 and a period of around 1.4 microns. So again, low aspect ratio, and in that case we get an enhancement of around 20%. And if we look at sort of very high aspect ratio structures, which might be more difficult to fabricate, in that case we can get enhancements of up to 35%. So that would obviously be a very significant boost. So we can look at the absorption spectrum for a particular geometry. In this case, period of 800 nanometers for the grating, height of 1600 nanometers. So shown on the dotted line is just the absorption of the PDTP in the planar case, and then the green here shows our absorption in this nanostructured case. And so obviously we get significant enhancement at all wavelengths. You can also sort of see where the losses are occurring in this cell. So shown in red is parasitic absorption due to silver, light blue is parasitic absorption due to ITO, and then yellow would be reflection losses. So this gives you a feel for sort of where are losses occurring in these cells. We can also look at the field intensity distributions. So again, we look at this particular case, 800 nanometer period, 1600 nanometer height. So we look at two wavelengths, and we can just look at the field intensity distributions in the cell. So if we look at, say, 600 nanometer wavelength. So this is our grating here. We have a thin layer of the PDTP. So the first thing to note is we do get some enhancement in the field intensity. So this map shows field intensity normalized to the incident intensity. So we have enhancement of around 4 times. The other interesting thing to note is the white vectors here show the Poynting vector field. So what you can see is that the energy is coming down into the cell and it's actually being expelled both of the zinc oxide region into the active layer. So this is helping with our enhancement. Much more interesting though is what's going on at 930 nanometers. So here, first of all, you can see the scale is much bigger. We have around 57 times enhancement in field intensity. So we're getting a very strong enhancement in field intensity. Also, interestingly, if you look at the Poynting vector field, you can see instances of vorticity. So this is sort of a hallmark of these kind of photonic crystal light trapping states where you have, when you have vorticity, you end up with very long-lived photonic modes, and that allows you to get significant enhancements in absorption. Right, so we also looked, as I said, at triangular corrugation. Basically, we just added a simple triangular pattern to the top of the cell to reduce reflection. And in this case, you can see this is the same plot as before, the same structure, but with the triangular corrugation added. And you can see that reflection losses have been essentially eliminated. There's a small amount of reflection here still, but for the most part, triangular corrugation is an effective way of introducing anti-reflection if you can manufacture it. So if we look at, so basically this is essentially an ideal structure from an optical point of view. This is the best that you can get with PDTP. I mean, you're always going to have parasitic absorption due to silver and due to ITO, but basically we've eliminated reflection and we have very high absorption across the board, which then falls down to 0 around very sharply around 950. So from an optical point of view, there's not much more you can do than this with PDTP. So to just pick out a few specific geometries, again, with a period of 800 nanometers for the grating and a height of 1600, we get a 38% increase in MAPD above the planar. For a period of 1200 nanometers and a height of 500 nanometers, which again would be a lower aspect ratio structure that could possibly be easier to fabricate. Even in that case, we still get a 25% increase. So we're seeing significant increases. One other thing I wanted to talk about is off-normal performance. So our device shows very good performance at off-normal angles of incidence. And I think that's maybe one thing that's sometimes underappreciated with tandem cells is that you can create a great tandem cell that has excellent current matching at normal incidence, but then if you go to off-normal angles of incidence, it can lose that current matching. In fact, it probably will. So this was just a quick simulation I did of the two red curves here are 2 layers in a planar tandem cell. So I, simulated a planar tandem cell. I adjusted the layers until they were current matched. And then I looked at off-normal angles of incidence. And you can see that our top layer, in this case, which was P3HT, this is the relative MAPD normalized to at 0 degrees incidence. For one layer, the MAPD increases, for the other layer, it decreases, and of course, in a tandem cell, you're going to be limited to the current of the lower active layer. So in this case, you would see sort of performance falling off fairly quickly, whereas with our nanostructured cell, we have very good performance out to angles of around 70 degrees. So just briefly, this is sort of some recent results. I wanted to talk about a 3D structure that we've been looking at. So this is a slanted cone structure. It's based on some of our group's previous work with silicon, which I think you'll be hearing about in the next couple talks. So these are sort of conical pores arranged in a square lattice in a silver background. And we actually, for these 3D calculations, we switched to a new polymer called PTB7. This material is used in a lot of the highest efficiency single junction cells now. And since we've sort of already gotten all that we can get out of PDTB, we thought we'd switch to this new material. So, so for these 3D calculations, we actually use finite difference time domain calculations. If we just take, say, a planar structure, we get an MAPD of 19.1 milliamps per centimeter squared. And just, we choosing a particular geometry, a cone period of 700 nanometers, a height of 750 nanometers. So a fairly low aspect ratio structure, actually. We get an MAPD of 25.5 milliamps per centimeter squared, 34% enhancement. So this is just sort of some initial calculations, but we think there's a lot of room for much higher enhancement than that, especially since the absorption curve for this material has sort of a longer tail. It doesn't fall off as quickly as PDTB, which gives us more room to play with from a light trapping perspective. You can get enhancement over a wider region. You can see here, even at 930 nanometers, very low intrinsic absorption, but we get absorption above 0.6 or so. So conclusion. So we've demonstrated numerically that this 2D design can provide absorption enhancements of up to 40% in a low bandgap polymer solar cell. It has a conformal active layer, so it doesn't necessarily come at the cost of electrical performance, excellent off-normal performance, and our 3D studies show promise for even larger absorption enhancements with PDB7.